Hi, my name is Kritika and I am from the Machine Learning Lab. Our work is on privacy attacks in reinforcement learning. Reinforcement learning is applied in many real world domains with rich environments that contain sensitive user information. Some such domains are autonomous driving and recommender systems. We need to ensure that the private optimal policy learned does not memorize the sensitive reward function. So, we evaluate private RL policies at how effectively they protect the underlying rewards. Our work introduces the first privacy attack in reinforcement learning, the reward reconstruction attack. It tries to reverse engineer the reward from a private policy using inverse RL algorithms. The attack is the key part of the novel privacy aware inverse RL analysis framework or the PRIL framework. We assume that the entire process and the optimal policy is released publicly. Differential privacy is a system for publicly sharing information about a dataset which masks individual contributions while retaining the big picture. And it does so by adding some noise to the data. The privacy loss is mathematically quantifiable and composable across queries. In our work, the agents learn optimal policies by exploring the environment and taking in sensitive rewards as feedback for their action. Two reward functions are said to be adjacent if the maximum L2 norm of their pointwise difference is upper bounded by 1. There exist multiple differentially private RL algorithms that preserve the privacy of the policy. Given an optimal policy for an MDP environment, inverse RL algorithms reverse engineer the hidden reward function used to learn the policy. Inverse RL is used to reconstruct the private reward function. It reverses the RL problem and tries to extract the reward function from an agent's observed behavior. We use this method in finite state spaces to reconstruct the reward by solving a linear program. We thus perform the reward reconstruction attack to determine how effective a private policy is at protecting the reward. The PRIL framework then computes the reconstructed reward's similarity to the original private reward via variance distance metrics. The system takes as input the original reward function and the private policy, and using the algorithm, it predicts the reconstructed reward. And then it finally computes the distance between the original and reconstructed rewards and compares this distance with other similar distances computed from private policies with varying privacy budgets. The larger the distance, the stronger the privacy guarantee in protecting the reward function. We demonstrate our results across 24 environments, 3 RL algorithm classes, 5 privacy techniques, 9 budgets, and 4 distance metrics. This includes the no privacy case as a baseline where the budget is infinite. The first graph shows the L2 reward distance across budgets for each private policy. It shows that there is no indication of the policy improving at reconstructing the reward with a relaxation in budget, thus rendering all strategies ineffective at providing true reward privacy. We need to ensure that the private policies provide meaningful reward privacy while simultaneously not compromising on the agent's utility. The second graph shows the privacy utility trade off for all policies. Here, the utility is the policy's average return during test time over multiple trajectories. From the qualitative heat maps, we can infer that agents are able to learn the true reward structure quite easily. Thus, our attempts to preserve reward privacy by enforcing privacy in policy are in vain. Based on the experiments performed, we can say that there exists a significant gap between privacy in policy and the privacy achievable in reward. We also infer that private deep RL policies are more generalizable. We find our results to be similar to the baseline case of no privacy. We look forward to any questions and discussions. Thank you.